The law of mass conservation is a fundamental law of chemistry, and its discovery could perhaps be called the starting point in the development of chemistry as a science. It provided early experimental evidence in support of the atomic hypothesis, the statement that all ordinary matter is made of atoms. It also suggested a universal rule that all chemical reactions obey. Let us consider the experiment that led to formulating the law of mass conservation. It is an experiment that we are very familiar with by now. The heating of a metal in the presence of oxygen that results in the formation of a metal oxide, but with one modification. The metal and air are heated in a closed flask. At the beginning of the experiment, a known mass of metal is placed inside a flask, and the flask is closed with a stopper. Because the flask is closed, whatever air is present inside the flask remains inside it and can't get out, and no air from outside the flask can get in. We weigh the closed flask with the metal and air inside it and record its mass. Then we heat the closed flask until the metal inside turns into an oxide. At that point, we weigh the flask again without opening it, and find that its mass is the same as it was at the beginning of the experiment. Now let's open the flask and weigh the metal oxides that we have formed. As we already know, its mass is going to be larger than the mass of the metals that we initially placed in the flask. The oxide formed by attaching oxygen atoms from the air to metal atoms, and the added mass is the mass of oxygen. So if the oxide is heavier than the metals that we placed in the flask, but the mass of the closed flask before and after forming the oxide was the same, what can we conclude? Pause the video for a moment and see if you can figure it out yourself. The mass of the flask itself and the stopper shouldn't change in the course of the experiment. Therefore, if the mass of the closed flask with its contents before and after forming the oxide is the same, but the mass of the oxide that we got is greater than the mass of the metals that we put into the flask, it means that the mass of whatever else is inside the flask at the end of the experiment must be smaller than the mass of whatever else was inside the flask at the beginning of the experiment. So what apart from the metal was inside the flask at the beginning of the experiment? Air. As you might know, air is a mixture of several gases. About 78.09% of it is nitrogen, M2, and about 20.95% is oxygen, O2. About 0.93% is argon, Ar. Argon is a noble gas, so its atoms already have octets and do not form diatomic molecules. Argon gas consists of individual argon atoms. About 0.04% is carbon dioxide, CO2, and there are also very small amounts of other gases, as well as some water vapor. And like all ordinary matter, air has mass. You can see that by comparing the masses of a full balloon and an empty balloon. At the beginning of the experiment, the air inside the flask came straight from the atmosphere. However, when we heated the flask, some of the oxygen molecules in the air inside the flask broke up into oxygen atoms, and these oxygen atoms bound to the metal atoms to form the oxide. As a result, the air inside the flask at the end of the experiment has the same amount of nitrogen, argon, carbon dioxide, and all other gases as it did initially. These gases didn't participate in the chemical reaction. However, it has less oxygen than initially. because some of the oxygen was taken out of the air and attached to the metal to form the oxide. To be precise, because the mass of the closed flask before and after the chemical reaction inside is the same, the mass of oxygen that is removed from the air inside the flask is exactly the same as the mass of oxygen that is added to the metal oxide. More generally, the total mass of all reactants in a chemical reaction is always the same as the total mass of all products. This statement is known as the law of mass conservation. In other words, ordinary matter may change form, but it is never created or destroyed. Atoms are never created or destroyed. This idea may seem common sense, and indeed it had been assumed in many cultures since ancient times. In ancient Greece, it had been stated by the philosophers Empedocles and Epicurus. It can be found in the writings of the early Jain philosopher Maswati and of the Persian scholar Nasir al-Din Tusi, who is best known as the creator of trigonometry. However, at that stage, it had been an assumption that had still to be verified experimentally. It was first demonstrated in the 18th century by the Russian scientist Mikhail Lomonosov, using the experiments that we described, and later established using similar but higher precision measurements by the French chemist Antoine Lavoisier. Although the law of mass conservation does not unequivocally prove the atomic hypothesis, it does provide crucial evidence in support of it. In particular, the fact that in a chemical reaction, the total mass of all reactants is the same as the total mass of all products suggests that the reactants and products are both built from the same building blocks, atoms, that are combined in different ways. This conclusion is reinforced by the law of constant composition, that, as you hopefully remember, states that all samples of a given chemical compound, regardless of their size, are composed of atoms of the same chemical elements at the same ratios. The laws of mass conservation and constant composition, therefore, served as the foundation of modern atomic theory that was first systematically developed by the British chemist John Dalton.